Alright, so we have 12.9 here, and we have what's called a Dirac delta function. That is what this symbol up there means, and I'm using it here and here for the first problem. So basically what that means is that if you were to take, an integral from, say, point A to B, and you have a Dirac delta function, I can't really draw it, of t. Whatever's in this function must be within the bounds of a to b. If it is not, then it equals 0. But if it is, then it will equal whatever the function is at whatever value t was. And I'll show you what that means, or what that really means. So basically what I want you to get is if, for example, this function, that Dirac delta function, is t equals 2, right? That is within the bounds of -2 to 4, so that will not be a 0. It ends up being a function, right? And I will go into details how to solve it in deeper. So, your first step really is to see how to solve the Dirac delta function. You need to figure out what it is equal to at 0. So this is equal to 0, since that gets a 0 inside that function. So we get a function of 0, that's what it turns into, times t cubed plus 4. And this one we'll say is a function of 2. So, since this function up here, when you solve for it, it gives you 2. So it turns into a function of 2. That's what I mean. Times 4. So what we're going to do is distribute that t cubed plus 4 to both of these. And that, as you can see, will be a function that you're solving for. You plug it in. So t cubed at 0 is 0 cubed plus 4, plus this one evaluated at 2 will be 2 times 2 times 2 is 8, plus 4 times 4. Then you have this integral from -2 to 4. Okay. So the thing about this function is when you apply an integral to it, right, you have an integral of, say, some function of t times a Dirac delta function. I don't know how to really draw it. I'm going to explain how we get rid of this integral of t, we'll call it, from -infinity to infinity, dt. This turns into whatever that function was equal to at 0, which is what the Dirac delta function was, that function at 0, times 1. Because this evaluates to 1. But the special thing about the Dirac delta function is that it only will exist at wherever this function will be equal to 0 from what you got from the Dirac delta function. That sounds a little complicated, but you kind of see what we did in the process here. So this integral is canceled out by the Dirac delta function. You're not even really worried about that. So what you're doing is basically solving now. So you got 32 plus 16 plus 4. We get 48 plus 4, that's 52. That's our answer for the first one. Now let's do the second one. Okay. Let me draw it real quick. Okay, so now we have this next set of problems here. So first we're going to distribute this t squared to everything to make it look nice and good. So we got this plus t squared Dirac delta function of t plus 2.5 plus t squared t minus 5 dt. The integral over here. Okay, so now we're going to evaluate it and go into each individual part again. So this Dirac delta function at 0 is going to be 0 since it's just t. So this integral will transform that function that it's equal at 0 basically into f of 0 t squared plus this one at 0 is negative 2.5, so we get f of negative 2.5 t squared plus this one's going to be f at 5 t squared. Now that integral gets canceled out because by turning this in each and every one into functions, that kind of where only the Dirac delta function will exist. And basically, how to sum it up in a way that I understand it is this: since everything's multiplied by the Dirac delta function, it can only exist within where it's real. And where it's real is where this inside function is equal to 0. Kind of deal. And you need to just get the basic premises that it turns into the whatever that function is equal to at 0. Hopefully that makes sense. So f at 0, or t at 0 will be 0 squared plus negative 2.5 squared plus 5 squared, which is equal to 25. This is, let me think, 6.25 plus 25, which is 31.25. And that is how you do that.